Hello everyone and welcome to AceOSCE's video for today. This is Alicia. Thanks for joining me. Today I'm going to have a quick review of pharmacokinetics, just the next part of it, which is metabolism. This is video number 4 in my pharmacokinetic series, and just reminding everybody that this is a quick overview of each topic in the pharmacokinetic series. It is really hard to assemble a full overview video, so it's just a quick overview, just the basics. So let's get started. We are going to be going through a quick overview of part 4 of a pharmacokinetic basics, that is metabolism. Let's have a quick look at what metabolism is and what it entails. So usually metabolism is the chemical modification of a drug to transform it into a form that may be easily eliminated from the body. Usually whenever a medication is more water soluble, it is more readily excreted by the kidneys. Therefore, usually metabolism aims at making a drug more polar or more water soluble. This process usually occurs in the liver, and mostly it uses the help of enzymes. We will be discussing a little bit more in the further slides about this. Now, metabolism can happen in two separate phases. It can either be phase 1 reactions or phase 2 reactions. Let's have a quick look as to what these entail and what these phase reactions mean. Usually, phase 1 and phase 2 metabolic reactions are both intending to make the drug more water soluble or polar to aid in renal excretion. So here we're only talking about renal excretion, which is usually the case in which medications are excreted through the body. These are usually complementary and sequential. So some medications may actually go through phase 1 and that's it. But that's a very few medications. Usually medications go through both the phases, phase 1 and then phase 2. So these are not usually exclusive pathways. These are sequential and complementary pathways in most cases. As you can see in the diagram at the end of this slide, the active drug is usually acted on by phase 1 medications and then phase 2. Now, metabolism for phase 1 reactions first of all makes the drug polar by either adding or unmasking functional groups such as OH and SH. The most important in this case is oxidation. The metabolites are usually inactive. Of course, there are exceptions in which case some drugs may be actually metabolized to form the active drug, but this is more like a generalized statement. After this phase, the drugs are usually sufficiently polar to be excreted readily, and usually cytochromes elicit oxidation. So oxidation is the major pathway for phase 1 reactions, and cytochromes or enzymes, they are the ones that execute this oxidation for most medications during their metabolic phase. Usually cytochromes are enzymes that help in metabolism. For example, the P450, and this is the one that acts on most medications. The cytochrome family of enzymes is the most vast family of enzymes that helps in phase 1 metabolic reactions of most drugs. These are usually found in the liver, lungs, kidneys, or even the placenta. It consists of more than 50 isoforms. It is the major source of catalytic activity for oxidation, which again, to remind you guys, is the most important or the most extensively used pathway in phase 1 reactions. And just to kind of give you guys a little bit of a heads up, it has different efficacy and different populations in people. So when you study about certain medications, you will realize that the cytochrome P450 or cytochromes in general may have different rates of metabolism or activity in different populations, especially some regions like Asian populations or American populations or African populations. So whenever you're reading about medications, do keep this in mind. The 6 main isoforms are listed here, the most important of which is 3A4. Phase 1 reactions, again, the cytochrome family of enzymes. I just wanted to discuss quickly about inhibitors, inducers, and blockers. Now, medications that inhibit the enzyme action, in this case the cytochrome enzyme action, do result in the prolonging of the action of the drug, and in some cases increase the level of the drug to toxic levels and result in toxicity. Inhibitors of these enzymes, for example ketoconazole, cimetidine, and amiodarone, they inhibit the reaction of these cytochrome enzymes, which is why medications may not be actually metabolized as fast as they should be. Inducers, on the other hand, are medications or drugs or chemicals that induce the enzyme action and increase its action, Therefore, shortening the duration of action of a drug may cause suboptimal effect of the medication as well, most common ones being phenytoin or carbamazepine. In contrast to these two things, there's something called blockers. These drugs act on non-microsomal enzymes. Now, metabolism phase 2 reactions. Phase 2 reactions are actually the true detoxification reactions that make a drug ready for excretion. So in this phase, there's not just a transformation of the medication itself. Usually there is some sort of attachment of a group or some sort of chemical transformation of the entire drug, which is quite major, which makes this medication even more readily excretable in the kidneys or renal excretion. Types of phase 2 reactions can be classified as either glucuronidation, which is the most common pathway in the phase 2 reactions. There's sulfonation, acetylation, amino acid or condensation reactions, conjugation reactions such as fatty acid, glutathione, and amino acid conjugations are other examples of phase 2 metabolic reactions. Just keep in mind that if you ever get a question in PEBC about which one is the most common or most extensively used, it's the glucuronidation. We are going to be studying a little bit more about glucuronidation in this slide. Quantitatively, it is the most important phase 2 reaction for drugs or endogenous compound excretion or metabolism. So in terms of quantity or the number of medications this pathway metabolizes, this is the most extensive one. It is the products that are formed after glucuronidation are usually excreted in bile, and this is the structure of the glucuronic acid. There are a couple of different topics I wanted to quickly go through with you while we're studying metabolism. The first one being first pass metabolism. Now, when the drug gets metabolized at a specific location in the body, that results in reduced concentration of the active drug upon reaching its site of action or systemic circulation. So even before reaching the site where it shows in action, it is already metabolized, which is called as first pass metabolism. It usually occurs in liver and may also occur in the lungs or the GIT tract. So this is an important thing to know. If you ever get a question about this, it can also occur in the lungs or GIT, not just the liver. Now, this may be bypassed by giving the drug either SL or IV. For example, insulin, lidocaine, diazepam, and ethanol, all of these undergo extensive first-pass metabolism, which is why they are best given in either SL or IV forms. And one of these questions that I posted was regarding first-pass metabolism as well. So keep this concept really clear. The second thing I wanted to discuss was plasma protein binding. Now, this is more into the distribution phase, but I think I may have skipped this in that slide or that video, so I just wanted to account for that here. So plasma protein binding usually occurs when a drug binds to plasma proteins in the plasma or bloodstream. This may reduce its activity because its free form is not available to elicit the therapeutic effect, and it may limit the drug distribution, therefore affects the drug metabolism. Now, for most plasma protein bound medications, or most famous ones, are diazepam, phenytoin, and valproic acid. There may be others as well, but these ones, kind of just know general knowledge, may get a few questions, maybe even case-based questions about how these medications may have a plasma protein binding or which ones don't have more plasma protein binding, and again, unavailable to exert the therapeutic effect in most cases. So an important concept to keep in mind. So now that we've gone through basic metabolism like an overview, I had a quick question, and the question for the topic today is: the Tina has been stable on her candesartan, rosuvastatin, and metformin for 3 months. The addition of which of the following medications may increase levels of her chronic medications in her blood? Erythromycin, dactinomycin, tobramycin, and azithromycin. Giving you guys a quick hint to read the question really carefully and understand what the question is asking out of you, and have a look at the options nicely before you answer. Again, I hope this video kind of helps you. It was a quick overview about metabolism. Definitely a lot more to cover, but already a 10-minute video. Definitely reach out to me in case you'd like to know more, take classes, or even many mock tests. Feel free to reach out to me on the platforms listed here, and I'll see you guys in the next video. Take care until then.